Okay, there were quite a number of students who were telling me that they couldn't obtain the pi from arctangent 1. Don't forget that arctangent 1 is not equal to pi, it is pi over 4. So you have to multiply arctangent 1, whatever value you obtain, by 4 to obtain an approximate value of pi. Okay, so today we will continue with the Gauss law. Okay, I hope you are not getting bored of the Gauss law, but I will repeat what we had done in the Gauss law. First of all, the concept of flux. Now, in terms of the field line, the flux is basically the count of number of lines you have for a given convention. And the flux for the electric field we had defined as E dot dA. So what you should understand from this one is if you have an arbitrary surface and there is some arbitrary electric field in the region where you have this surface, you divide your surface into small parts. If the patches are sufficiently small, they will be flat, almost flat. If they are flat, you define the dA to be perpendicular to the area. To that flat area. It is perpendicular and its magnitude is equal to the area. So we know the magnitude, we know the direction, there's an ambiguity there's an arbitrariness in the direction. You can choose the direction in both ways. If you have a surface, there are two perpendicular directions, one pointing in this way, the other one pointing in this way. So you are free to choose both of them. One thing you have to pay attention to is that if you choose this area in this direction here, in the next patch, you should also choose it in the same direction. I mean, once you choose it once for a given surface at a given point, and that fixes the direction of dA at every point on the surface. Now, once you have defined these dAs, at the same point, you can calculate the electric field. This is the electric field at exactly the same point. So you have the electric field vector, you have the dA vector, you just take their scalar product and sum over them. This is how we define the flux. Now the reason why I'm insisting on this, repeating this definition, this discussion of the flux, is that flux will be a concept that we will be using throughout this semester. Not just the electric field, we will be also talking about the magnetic flux, etc. So it's important that you understand the concept of flux. Now, any questions on flux? Gauss law is basically based on this concept of flux. Now, the flux you can define for any area. It doesn't have to be a closed area. It can be any surface. You can also define the flux going through a closed surface. This is equal to the charge inside divided by epsilon 0. Now the charge inside, what we mean by inside of a closed surface, is determined by your choice of the area, dA. These elements dA, these vectors dA, they point from the inside to the outside. So if you have a closed surface, your choice of the direction of dA tells you what is the inside your surface, what is outside your surface. So if there is some charges inside your surface, then this integral of the electric field over the all of closed surface gives you the total charge, should give you the total charge. There is no ifs, there is no onlys. This is valid in every case. Whether you have metals, this is valid. Whether you have insulators, this is not valid. Whether you have some other exotic material, this is valid. Whether you have moving charges, we will see that even for moving charges, this expression will be valid. So this is valid at all times. Are there charges outside your area which determines the electric field? Fine, this is still valid. If you have charges outside your closed surface, then of course the electric field will receive contribution from those charges outside your surface, but nevertheless, this integral will only and only depend on the charges inside your surface. And if there is no charge inside your surface, this integral will be zero, and that doesn't mean that the electric field is zero. It only means that this scalar product is positive in some areas and it's negative in some other areas.
Hocam, Lux'ı sadece matematiksel bir araç olarak mı görmemiz lazım, yoksa tek başına fiziksel bir anlam ifade ediyor mu?
Yeah, I would rather if you keep it just as a mathematical tool. It's a mathematical tool, just like the field lines. We had just invented them to help us visualize the electric field. The flux is also similar. We will see some other applications of it towards the end of the semester, which will give it some more meaning. But for the time being, just keep it as a mathematical tool.
We taken charges as point objects, but we know they are not points in real life. So, when real applications, how can we define the charge enclosed from utilizing that charge enclosed?
Well, you see, as you said, the charges are not point objects, but the this is a mathematical surface. It has zero thickness. So there's no problem of defining the charges inside and charges outside my surface.
Charges are two-dimensional objects.
Okay.
We can talk about outcome.
Okay.
So, a surface that is going inside of the charge.
So let's look at this example. We have a sphere of radius r. So what is the electric field everywhere? Now, whenever I say you have to find the electric field everywhere, I mean, you should give me an expression that is valid. If I choose such a point, if I choose this point, etc., it should be valid at every point in space. And there is a uniform charge distribution. So how can we find the electric field? Now, in the application of Gauss' law, remember there are two steps. One, identify a suitable Gaussian surface. That is our first task. What kind of a Gauss surface we can use and why. And the second one is just apply Gauss' law. Now, how can we determine on the Gaussian surface? Let's say I want to find the electric field at this point. Now, to be able to identify a suitable Gaussian surface, first of all, we have to know something about the electric field created by this charge distribution. So what are some of the properties of the electric field that is generated by this charge distribution? Let's assume we don't know anything. The only thing we know is that the laws of physics are invariant under your choice of coordinate system. So let's say we have this system. Let us suppose that I take my whole system and rotate it around its center. So does the charge distribution change? Or if I rotate it like this, or in any other way, whatever rotation I consider about the charge distribution around its center, the charge distribution doesn't change. So the electric field should also have the same property. Because as I'm changing the charge distribution, rotating the charge distribution, I should be also rotating the electric field at the same time created by the charge distribution. So if the charge distribution doesn't change as I rotate my charges, the electric field also cannot change. So that already tells me that the electric field has to be in the radial direction, just like the point charge. Because that is the only configuration which doesn't change under arbitrary rotations around the center. I know that the electric field should be in the radial direction, that is one thing. Its magnitude also can only depend on the radial distance. It cannot depend on anything else. So those are the two informations I have. Now to be able to, okay, Gauss law is valid for every surface. But of course, being valid doesn't mean it will serve our purpose. If we choose an arbitrary Gauss surface, let's say something like this, okay, the Gauss law will still be valid for the surface, but we cannot really make use of it. Now, to be able to use the Gauss law, let's look at this one. We have to find somehow some surface for which the electric field is either constant. Let's say this is what we are trying to evaluate now. So we have to identify a surface at which either the electric field or its magnitude, let's say, is constant, or the scalar product should be 0. So that way we can just simplify this integral. Now if you look at this electric field, we already know how it should, some properties of the electric field, just looking at the symmetry, because things do not change as we rotate them. So if we always stay at the same distance from the center, if R is the same, the magnitude doesn't change. dA is also in the radial direction. If we choose a sphere, dA would also be in the radial direction. So the angle between dA and the electric field is the same at every point. The magnitude of the electric field would be the same at every point if we choose a sphere around the origin. Now I want to find the electric field at this point, so my surface should better contain that point. So this is my Gaussian surface. Okay, that is the Gaussian surface that I will be using. Why? Because it's a sphere, so every point is at the same distance from the center, so this E of R is a constant as I'm taking this integral. Every constant I can just take out of the integral, so this I will be able to take out. dA will be in the direction of R hat, so the angle between dA and R hat will be 0 all the time, wherever I am on this surface. So that will simplify my integral. Now, dA would be its magnitude in the radial direction because I chose a surface, a sphere. And so E dot dA would be the magnitude times dA. So this radius of my Gaussian sphere, let's just call it small r. Now this integral, the Gaussian integral E dot dA, would just be the integral of the magnitude times the dA, the magnitude of dA. Now I said that at every point on my Gaussian surface, this is just constant. So I can just take it out. This is E of R dA. Now this is sum of all the patches making my sphere. Sum of the areas of all the patches making my sphere, but that would just give me the total area of my sphere. This is E of R 4 pi r squared. So this is the integral of the electric field over the area. Now the next thing, what is the total charge enclosed? What is the total charge inside my sphere?
This is all times x10
No, I mean, okay, I will equate this expression to something else that I know. I have to write the total charge enclosed by using the quantities that I already know so that I will be able to calculate this E of R. So I already have, you see, we have the Gauss law, which tells us that E dot dr dA integrating over a closed surface is Q enclosed divided by epsilon 0. And what we are trying to do is to obtain the electric field. We already know its direction. We didn't obtain it from the Gauss law, we obtained it from using the general properties of the charge distribution. We already know the direction, we need to find the magnitude of the electric field. And to find the magnitude of the electric field, we will be using the Gauss law. So we had evaluated this left-hand side in terms of our unknown that we are trying to find. So we have to express the Q enclosed by the quantities that we already know. So that by solving this equation, we can find our only unknown. So somebody was saying the 0. Why? Now, if you remember, we had this shell theorem, which said that inside a spherical shell, if it's uniformly charged, there's a uniform charge distribution on the surface, the electric field inside is 0. So if this wasn't a volume, but just a shell, a spherical shell in which the charge distribution was only on the surface, then we already obtained the shell theorem. Because this should be 0 because there's no charge inside the shell. So this would have been 0 and ER should have been 0. Inside the empty shell, the electric field, the magnitude of the electric field would be 0. So we have the proof of the shell theorem. But here this is not a shell. This is a volume which contains a charge uniformly distributed over the whole volume. So what is the charge? So what do you understand by uniformly distributed charge? What does it mean to be equal at everywhere? What does homogeneous mean? So what is a charge density? What is this rho? We said that there is this rho charge. This is the charge density for the charge distributed over the whole volume. What do you understand by charge density? What is the charge density? Charge per unit volume. So if you take a unit volume, you calculate the charge in it, what you will find is rho. So if you have 2 units of charge, 2 unit volumes, the charge inside those 2 unit volume will be just twice the rho. So here we have a volume. What is the volume of this sphere? 4 over 3 pi r cubed. That's the volume. We know the charge density. So Q enclosed will be 4 over 3 pi r cubed times rho. This is the enclosed charge by our Gaussian surface. This blue sphere over there. We have this imaginary surface. Inside of it there is a charge distribution with a charge density rho. And all the volume inside our sphere has this much charge. Now we can use the Gauss law. We know both sides of this equation now. So we know that E of R times 4 pi r squared is equal to 4 over 3 pi r cubed rho times 1 over epsilon 0. And we can also cancel, make some simplifications. This 4 pi will cancel this 4 pi. E of R is just rho over 3 epsilon 0 R. So electric field increases linearly as you go from the center towards the surface. Now this is one part of the solution. So this is the electric field at a point inside my sphere. Now we can look for a point outside my sphere. So this is my sphere. it has a charge density rho, I can say that I can ask for the electric field here. Now let's go back. Part of this result we can also use if we are outside. Well, the electric field should have this property everywhere. This property is valid. So E dot dA everywhere will have this expression. So this is the left-hand side of the Gauss law. We'll still have this expression whether we assume a sphere inside whether we assume a Gaussian surface inside our sphere or out of our sphere. Up to this point, nothing changes. The only thing that will change is the enclosed charge. Now, since all the charge is enclosed, what will be the enclosed charge? Volume times rho. Volume is 4/3 pi capital R cubed. So I will take this one, E of R times 4 pi R squared. This should be equal to 1/epsilon 0 times the total charge in my sphere, 4/3 pi R cubed. Again, I can make certain cancellations. Rho, correct? So E of R is equal to 1/3 epsilon 0 rho. This time it is R cubed over R squared. So we have these two regions. This is valid if R is larger than capital R. We are out of our sphere. And this is valid if R is inside my sphere. So I can just combine my results. E of R, the magnitude of the electric field, is equal to rho over 3, no, let me also take the rho over 3 epsilon 0 outside. Rho over 3 epsilon 0 times R, if R is inside my sphere, and R cubed over R squared is R is larger than outside my sphere. Now what happens when R is on the surface? If I'm on the surface, well, both of them give the same answer anyway. The electric field is continuous. So I just pick anyone. Now, before we continue, just look at this expression over here. This one. Again, that is the other part of the shell theorem. So this is the total charge. This is Q over epsilon 0. If you just move the 1/4 pi R squared to the right-hand side, you get the electric field outside is 1/4 pi epsilon 0, total charge of the sphere divided by R squared. It is just as if the whole sphere is a point charge. So that was what the shell theorem also stated as. Outside of a shell, well, you can just imagine that this is just a collection of shells. If you are outside the sphere, all of the shells will just behave as if they are point charges right at the center of this shell, in the sphere. So this is the expression for that. So we, in a sense, using the Gauss law, we had already proven that we have the shell theorem. And here we don't have point charges. We assume that we have a continuous charge distribution. And at least in the previous part of the charge was inside my sphere, part of it was outside my sphere, my Gaussian surface, and I can still use the Gauss law.
Why the field increases linearly from inside?
Why? I mean, we have the Coulomb law, right? 1/R squared. The further away you go, the electric field should decrease. But not inside the sphere. Why not?
If it is uniform, so how it's increasing?
How it is?
Increasing, if the field is uniform.
Okay, any answers? The charge is uniform, not the field. The electric charge is uniformly distributed, not the field.
As well as it increases, the charge is becoming more relevant somehow increasing. The percentage of the increase of the charge is way bigger than the increase of the distance. That's why by applying the Coulomb law is increasing.
So basically the expression over here. You say this part over here is the Coulomb law, 4 pi r squared. Whereas this part over here is the increase of the charge creating the electric field, contributing to the electric field. So this increase is faster than this one. That is why inside the shell, you see, if you remember the shell theorem states that if you are inside a shell, the electric field is zero, created by the shell is zero. All the charges here, they do not contribute to the electric field on my Gaussian surface, or they do not contribute to the electric field at this point. All the charges in this shell, because I'm inside those shells. All the charges inside my Gaussian surface, they do contribute to the electric field at this point. Now, as you go further away from the center, your friend is right, we are going away from the center, so we should have this 1 over r squared decrease, and the contribution to the electric field of the charges over here, close to the center, they do decrease by 1 over r squared, but now there are more charges that contribute to the electric field, and they cause the net electric field to increase. So that's why inside the net effect of these two effects, on one side, as you go away from the center, the contribution to the electric field from these points will be getting less and less. But at the same time, there is more charge contributing to the net electric field. The net effect just becomes, the electric field becomes stronger and stronger as you go away from the center.
So it is the net electric field, not for the rest part?
No. This is the total electric field created by all the charges in our system. Inside and outside. Other questions? Let's do another example. The infinite wire. We had already solved this problem. We had calculated the flux created by the electric field created by this wire. But let's now go the other way around. Let's assume that we don't know the electric field of this wire, but we know the Gauss law. How can we use the Gauss law to calculate the electric field here? Now, the first thing we have to do, we have to analyze the electric field. What do we know already about the electric field by just looking at the charge distribution? What can we say about the electric field? For example, the electric field, can it point, I don't know, let's say in this direction? Is it possible that the electric field points in that direction? Why or why not? It's infinite wire. For the total electric field created by this infinite wire, which has a charge distribution, linear charge density lambda. Okay, that is one thing. That is one thing that we had already done in the calculation of the electric field. But that already assumes that we know certain things about the electric field. That assumes that we know the electric field of a point charge, for example. Of course, we calculated it, we do know it, but let's try to avoid any kind of electric field.
Is it because right-hand side and the left-hand side of the point is symmetrical to each other?
Okay, so if the right-hand side and the left-hand side are symmetrical, it will tell me that if the electric field at this point just points like this, the electric field here should also point like this.
No, I mean, up and down.
Okay, up and down, what do you mean by up and down being symmetrical?
If I take a point that is straight, and that line would be symmetrical always.
So what does it mean being symmetrical?
If I think about point charge, right?
Okay, you see, in these arguments, our magic word would be symmetry. But since it's the magic word, I have to make sure that you understand it. Of course, it's because of the symmetry, but what do you mean by because of the symmetry? How does the symmetry lead to the electric field not being in this direction? So you have to be able to build up this chain of thought. Okay, it's symmetric. What do you mean? What kind of symmetry it is? How does the symmetry lead to electric field not in this direction?
It cancels.
So what cancels what?
Itself.
So again, you are back to his answer, right? So a part from the top has the symmetrical part from the bottom. If you just sum them up, it will be in the horizontal direction. Okay, that we know. Some other explanation.
Takes me for the horizontal axis. The symmetry of the above and the up should be same.
So what does it mean? What does it mean? The symmetry of up and below is the same.
Above it is horizontal and
You can explain also in Turkish if you want.
mesela bir çizgiye simetri sağlarken simetri yaklaşan simetri birbirine eşit olmaz.
What do you mean by symmetry being equal? I mean, I know how numbers can be equal, but I don't know how symmetries can be equal. I know how symmetries can be equal, but not in this case.
Sonsuz olduğu için yani sürekli aynı elektrik olması gerekiyor.
So you are saying that the electric field should be the same everywhere.
If you take a point charge, its electric field is sphere. If we add them 1.1.1 with longer them up, it will be a cylinder.
How do you know?
Because a point charge, if you look everywhere, you said last lecture, the nature doesn't care how you look.
Okay.
So if we add them point charges infinite line, it will be a cylinder.
Why cylinder? I mean,
Because it's infinite. If it's not be a cylinder,
you see, let me just put it this way. Okay, let's just imagine this circle, and every point on the circle, the electric field lines are just like this.
no, I think
Then I can imagine this another circle over here. They all can look like this. Why are you against this one? What is wrong with this one? Based on your argument. I mean, the electric field lines do not look like a cylinder, by the way.
ya işte şöyle dışarı doğru itiyor ya.
What is pushing
Yani,
what?
yani hani nereden bakarsan bakalım küre oluyor ya.
Okay.
Küre şeklinde. Yani küreleri nokta nokta eklersek sonsuza kadar böyle uzuyor.
So your friend is saying that here I have a sphere for a point charge. Here I put another sphere.
Sonsuzluğa limit alınca öyle şey oluyor. Seviniyoruz.
I mean, that becomes a filled cylinder. You are filling every point inside. But what should I make about that filled cylinder?
Since the length of the wire is infinite, whenever point we choose, the length above and bottom will be
The length is infinite. You cannot talk about the equality of infinities.
okay. But there will be one point corresponding to the bottom that tends to the vertical compact of the electric field. So electric field can should be also all points.
Can you repeat once more?
Whenever point, whatever point we choose, there will be 2 points, one bottom and one top.
Okay.
It's
The sum of the electric fields created by those 2 points will just give a horizontal one.
yes.
Yes, the third same answer. Let me give you one more question then. I have this point. I'm interested in the electric field over here. Okay, we always chose the symmetrical cases. Let me choose one area over here of length dx and some other area over here. This is at a distance, let's say x, at a distance 2x. I will choose a length twice dx. For every segment over here, I can find such a segment, right? And if I add all these segments up to infinity, I get infinities in both sides. So I get an infinite wire, right? Now the electric field created by this one will be in this direction. The electric field created by this one will be in this direction. Will they add up to be horizontal? So that is kind of the shortcoming of this symmetry argument, kind of. You see, for every such point, I can find such a point, right?
If we look at it like this, it's pointing up. If we look at it upside down, it's pointing down. It's not supposed to.
So I see some of you was kind of getting it. You see, if I am interested in the electric field at this point, you see, if the electric field at this point is looking like that, I can just imagine that I can just turn around this point. If I turn around this point, the electric field at this point should be pointing like this. That is one argument. But the problem is, if I also look at the symmetry, what I'm imagining is I have this infinite wire. I rotate it around from this point. Nothing changes. The wire is still an infinite wire. But everything has been rotated upside down, so it should also be valid for the electric fields. So the electric field over here, well, I will be cheating a bit. The electric field just becomes upside down. Now, the electric field cannot be both up and down. So there's a single electric field at a given point. This is not a problem only if the electric field is horizontal. So this tells me that it cannot be tilted, pointed upward. The electric field has to be, at this point, horizontal. Okay, this is one thing I used. I just rotated the flip the charge upside down around this point. So nothing should change. So the electric field should be horizontal. But this still doesn't tell me that the electric field should always point from this point away. Now another thing I can do is I can take this wire and rotate it around itself. Still nothing changes. So if the electric field at this point is radially away, then as I rotate it, this electric field over here will be radially away at every point on this ring. And furthermore, since nothing changes, the magnitude of the electric field should also not change. So that tells me basically two things. The electric field is in a direction that is horizontal, that is pointing away from the wire, and its magnitude can only depend on its distance from the wire. So this you have to determine before using Gauss law. So we know Gauss law is valid. We will be applying Gauss law, but before using the Gauss law, we have to know something about the electric field. Now let's look at this. We identified that some of the properties of the electric field. Now, what kind of a surface should we choose? You see, this should be our guiding principle in determining the electric field, the surface, sorry. The Gaussian surface should be such that E dot dA, the electric field, its magnitude should be either constant, and the angle between the electric field and the area element should be constant or hopefully zero. That is one guiding principle in choosing the Gaussian surface. The second thing, the second possibility is that the electric field should be perpendicular to the area vector. Then there's no contribution. Now, if the electric field is in the draw direction, pointing away from the wire, now the area whose area vector is perpendicular to that one is 0? No. Cylinder? No. You see, I have this cylinder. If you imagine the cylinder, this is the area vector, perpendicular to the area, right? Electric field is in that direction. So electric field and the area vector are pointing in the same direction. What I'm looking for is a surface whose area vector is perpendicular to this rho direction. Upward or downward. So if rho is this way, dA should be like this. Well, dA is perpendicular to the area itself, so the area should be this one. The flat area. Okay, I can use a flat area for my Gauss surface. Okay, this is a flat area. But for a Gauss surface, I have to choose a closed surface. So just a flat area won't be enough for me. Now, this is one possibility. This was one possibility. I have to choose an area which is perpendicular to the electric field. The other good choice would be I have to choose an area that is such that the dA vector is in the same direction as the electric field. The electric field is in this direction. dA vector should be in that direction. Everywhere at the same distance. Well, that is basically a cylinder, the size of a cylinder. So that gives us the size and the top and the bottom of the cylinder. That is why for a wire we choose a cylinder, because you can divide the total area of the cylinder into 3 pieces, the top, the bottom, and the side. The top doesn't contribute because E is perpendicular to dA. The bottom doesn't contribute because, again, the electric field is perpendicular to the area vector. Only the side contributes, and on the side, since it's the same distance, every point is at the same distance from the center, from the wire, the magnitude of the electric field doesn't change, so I can just take it out of the integral. So that is why, for the wire, we choose this closed cylinder. Now, once you identify a suitable Gaussian surface, the application of the rest is kind of trivial. I mean, the most difficult part in applying the Gauss law is how do you choose a given surface? Now, let's see. E dot dA over the cylinder will be E dot dA from the top plus E dot dA from the bottom plus E dot dA from the side. At the top, this is the direction of dA vector. At the bottom, this is the direction of my dA vector. On the sides, this is the direction of the dA vector. Now on the top, the electric field, we had already said that it is in the pointing away from the wire, horizontal. On the top, this is the dA vector, this is the electric field vector. They are perpendicular to each other, so E dot dA is 0. On the bottom, this is dA. The electric field vector will be pointing all around, but nevertheless it will always be horizontal, and hence it is always perpendicular to this dA. This will give me 0. So this is 0. This is 0. I also know that on the side at least, this is the magnitude in the rho direction pointing away from my wire. I also know what the expression of the electric field is. If I take the scalar product of this one with this one, I get E of rho times dA. From the side. On the side, rho doesn't change. Every point on the side of the cylinder is at the same distance from the center of the wire. So E of rho is constant, and hence E of rho is constant. What remains is the area of the side of the cylinder, which is 2 pi rho. If we assume the height is h, 2 pi rho h. And this should be equal to the total charge inside my cylinder. Now, what is the total charge inside my cylinder? Remember, we had said that the charge density of the wire is lambda. So lambda is linear charge density, lambda times h. Lambda is just the charge per unit length. We have a height h of the wire inside our cylinder, so the total charge will be lambda times h. This is the enclosed charge divided by epsilon 0. And this gives us E of rho is equal to 1 over 2 pi epsilon 0, lambda over rho. And if you are asked to find the electric field, 2 pi epsilon 0, lambda over rho in the rho direction. Yes. No, this rho over here is this distance. The radius of the cylinder is rho. Other questions? Okay, let's give a 10-minute break.